at the end. All right, record. Okay, so good. This is a recording version of this first presentation of the ZoomAFM. Before we start, I will introduce a little bit who we are and why we're here. This ZoomAFM.com is a platform for us to organize and support users of the Agilent Technology Atomic Force Microscope. On one side, we have all the users of the Agilent Technology AFM. On the providers, we have myself. I'm a former application scientist of Agilent Technology, and I know how to operate the instrument. And we have Steve Raba, who is a former service engineer of Agilent Technology, and Steve knows everything about how to repair the instrument. And we also have XQ Tom. He was the former technical manager of Agilent Technology. There will be more people come join us. We're all Agilent Technology former employee. And after the Agilent stopped making AFM, we kind of go different ways. And then we live around the world, and hopefully we could organize together and gather to support the instrument. And while we are here, we like to support molecular imaging, Agilent, and Keysight AFM users, and we provide lectures and training. We could do repair and maintenance, and then some of you, if you have missing parts, we can also get those missing parts and for you, cables and detectors, so on and so forth. And the goal is we want to keep your instrument running for maybe 10 more years. So the purpose is to provide consistent support with easy to find communication, right? ZoomAFM.com, it is very easy to find. As long as you remember this name, and it's going to be show up on the YouTube also. Okay, so first of all, the lecture is not going to be too long, and the purpose is to stir up conversations and hopefully you can ask me questions and also ask questions that some of our engineers can answer. And these are the participants, ZoomAFM.com. It's a website, and you can see the link, and we've announced the next presentation, the line on this banner. And then NanoQ Technology is actually the website of NanoQ Incorporations. And then we have a lot of inventions and also a lot of businesses on this site. And Steve Raba's AFM repair business is registered as HomeQ SPM LLC. First time I met with Steve after he started, and I asked him, why do you have this such an interesting, funny name, HomeQ? And he said it's nothing funny at all. HomeQ is honor and courage. And then he also showed me his sword. Steve Raba actually turned out to be, he is a former Marine, and honor and courage, that's his slogan. So, you know, both of us, and then when in the future someone more joining, we're going to introduce more. Anyways, so again, let's introduce the Atomic Force Microscope, the essentials. I have a habit that when people ask me how to do a certain experiment, what parameter to put, I'm always hesitate to tell them what kind of parameter they're going to use, because it is sometimes very true, and sometimes a single parameter may not work on one situation, work on another situation. So I always start from the basics, essentials, and explain to you how those things work, and it's up to you to decide your own parameters. So it is more important to understand how does it work, and then you decide what to do yourself. So the essentials of the Atomic Force Microscope, when I give people a lesson about AFM, I always show up this image, and I will ask them, look at this image. This is a crystal. Can you tell what color is this sample? And then if the audience say, I don't know, and that's the correct answer, because AFM image is not a colored picture, and the color you see is artificial. I can get any color you want. It does not mean color. Here, the real nature of Atomic Force Microscope is actually a list lines of profiles. So the instrument using a probe to scan over the surface, and then will register a series of profiles, and we stack the profile together. We apply color associated to height, and this color associated height is rendered as a three-dimensional picture. So that's where the pictures come from. The real nature of data is really these profiles. Okay, so basics of the atomic force microscope. Here we have a sample, and there's a tip, and then the tip is tilted. This tip is always tilted. That's because we need to have incoming laser, outgoing laser to detect the vibration or bending of this cantilever. We call it the oscillation and the deflection. And then we have to have the incoming outgoing laser spot to be slightly angled from each other. So that's why the cantilever is always tilted. And also we need to have this tip, which is very small. We have the tip to contact the surface before everything else contact the surface. That's why the cantilever is always tilted. Sometimes 8, 9 degrees, 12 degrees, depends on the design of the instrument. So it is always tilted. And the tip is always tilted, protrude upwards, so it can contact sample before everything else contact sample. And you can have the detector, or the PSP.
We can hear you.
You guys lost your sound too? We lost your sound, Song.
Yeah.
You might have to log back on. Just hang on. He'll probably be back. Song, you're on mute.
Okay, you should be able to hear me now.
We hear you now. Thank you. Yeah,
okay.
We can hear you now.
Yes. My phone somehow stopped working. All right, I'm switching to computer sound. Okay, so here we talk about the instrument always have, let's put this on, always have a optical microscope, and this optical microscope is actually either it could be from the top of the cantilever, or it could also be from the bottom of the cantilever. Let me go this. So optical microscope, and we're gonna have a mechanical loop that will that will hold everything together. And a lot of the problems such as drift and noise could be from the mechanical loop. So that's one source of the drift and noise is come from this whole loop. Okay, this is the cantilever, and cantilever is actually made of silicon nitride, and about 100 micrometer long, several micrometers thick, and then 20 to 30 micrometers wide. And then this is a hair that's on the left. You can compare the size of the cantilever. So this is a side picture of cantilever, and then you look at the right-hand side, you can see the chip, the size and shape of the chip. The chip itself will have a little bit slope. You can see the little slope here, and there's a purpose of this slope. This slope is so that when you put this cantilever on the surface of something, if this is on the right-hand side up, where the tip is protruded into the air, so the tip is saved from contact, and then this way you can pick up with a tweezer. However, if you flip this chip and have it upside down, the tip actually crashes on the surface. You notice the slope is facing up. If you try to pick up with a tweezer, you cannot pick up anymore because of the slope. So that's a design of the slope, and it also allow you to identify the upper and down side of the cantilever with your naked eye. So you can see, if you can see shiny slope, you know that your cantilever chip is upside down. Okay, I'm going to skip all these and then go to the some of the parameters of cantilever. So we want to have a sharp cantilever, but we're going to define what is the so-called sharpness. The sharpness cantilever have two different ways to describe. And one way we describe is that we call the aspect ratio, which is height divided by the width. That describes how steep is this cantilever. And this is important for you if you want to use the cantilever to image something that has a deep hole in it. And we also describe very end of cantilever as if it is part of a sphere, and we put a sphere there, and the radius of the sphere is the indication of sharpness. Okay, that's why when we say it's a 2 nanometer cantilever or 10 nanometer cantilever, what we mean is the equivalent radius sphere, and how big is the radius. 2 nanometer is a 2 nanometer sphere. It's the radius. When you see a 50 nanometer, it's a blunt tip. Basically, that's equivalent to image it with a 50 nanometer ball in radius. Okay, so sometimes this is a SCM picture of the cantilever, and you can see this on the left is sharp, on the right somehow it is blunt. And then if we run a animation of this, you can see that the tip is actually traced along the radius of the particle we want to image. And if you look at on lower left corner, the actual image is the width of your particle plus the width of your cantilever. So if you have a dull, blunt cantilever, the particle is going to appear to be more thick than it is. If you look at this image, on the top part, you can see the little dots, and on the bottom part, those dots appear to be thicker. That is because your tip is crashed in the middle. Some tall structure hit the tip, and then the tip has become bigger, and therefore, when you're imaging the sample is also imaging your tip. The end result is the two structure combined together, and we call it convolution. Okay. This is an animation, shows how important is the aspect ratio. When you image something has a steep hole, a steep trench, you need to have a cantilever has a very tall aspect ratio. And tall aspect ratio allow you to reach the bottom of this trench. And then remember that if your tip is too thick, you do not reach the full bottom of this structure. So that's important that you have the aspect ratio as an indication or measurement of your cantilever tip. Okay, and you see that red line is the end image. And as you can see, the red line actually does not always represent the true profile of the sample. It also has a convolution. Okay, these are samples of cantilever tips, has very sharp points, and there's many different ways to reach this sharpness. And then when some companies sell you ultra sharp cantilever tips, that's what do they mean? It's extra sharp and has very sharp spike at the end. Okay, so when tip is imaging the sample, I'm going to draw these two graphics. It is going to start to experiencing attractive force when they're a little bit far away. For example, in this case, around a split of nanometer. But when this attractive force sometimes could act at much longer distance, as long as 10 nanometers. Especially when your sample, that's such as a polymer sample, has a big attractive long-range force. For a regular, sample with no charge, normally the tip sample experiencing attractive force within 1 nanometer. And then as the tip is invading the sample itself, it's going to switch to repulsive force, right here. And then we use these two kind of force to image the sample. So we have attractive force and repulsive force. Attractive force will cause the tip to experiencing a negative force gradient. Repulsive, the tip is experiencing a positive force gradient. And this is a very simple force curve, and you can actually show that you have attractive repulsive force. When tip and sample is far away from each other, it is a flat line. Tip is experiencing no force. When it's close enough, the tip will snap into the sample, and then if you push down the tip further, the tip will bend up, and then the force becomes repulsive. And then when you pull the tip away from the sample, you actually pull away. There is a strong adhesion force that pull the tip into the sample until the tip snap away from the sample. That's its contact mode force curve. Normally, when we using contact mode, the set point is actually slightly above this zero force line somewhere here. And then remember that when you have a higher set point, your force is higher. In AC mode, or sometimes we call tap-in mode, the tip is oscillating, and as it's oscillating, it will have a constant oscillation frequency as long as your driving amplitude. When your driving amplitude is a constant, your amplitude is a constant, and this is called a free amplitude. As the tip interacts with the sample, the amplitude will decrease because the tip is actually damping its energy into interact with the sample. And if we put a set point right here, a fraction of the free amplitude, and then we can control the tip sample at the separation distance, and then we can use that to image and scan the sample. And then in this case, the set point is always a fraction of the amplitude of free amplitude. So in AC mode or tap-in mode, a set point is always below the free amplitude. In contrast, in contact mode, set point is above the free deflection. Okay. And this slide shows how the how the piezo scanner works. A piezo is a material, you apply voltage, it will change its dimension. And as it changes dimension, you can use that to control the movement of the tip. Early time, the people use 3 piezo bars to control the XYZ. But later on, a piezo tube is used to scan the XYZ. Here's how it works. If we look at upper right corner, the tube is coated with electrodes on 4 sides, and if you apply voltage on the opposite side with opposite sign of the electrical voltage, the tube will experience internal stress, and therefore it's going to cause a bend because of stress, and this bending act as a scanning. And if you apply voltage universally, it will stretch and contract, which is called your Z scanning. And here's some drawings of a sample scan instrument, a tip scan instrument. So you notice I have a line here. That's because these scanners, they always have 2 portions of the piezo, and 1 portion is act as the XY, which you apply voltage opposite sign from the opposite sides, so the piezo tube will bend. And the other side, you apply voltage, section, you apply voltage universally. So it'll contract, expand. Now imagine, I mean, if you want a long range piezo scanner, your tube will need to be longer. So you see all the older design, you have a very long piezo tubes. However, imagine that if you can fold the upper part down, fold this XY down, you could make this scanner much shorter. And this is the design behind the Agent AFM scanner. In this case, you can see. See, these 2 piezo plates are the XY bending piezo, and then it's actually contract, expand on opposite side, cause the pendulum to swing. When the swing is translated to XY scan, and this Z piezo is translated to Z scan. So you can do XYZ scan at the same time, and the laser is actually part of the fixture of this, or fixed on the pendulum. So this to assure that the laser is always point to the exact same spot of the tip. So that's the scanner you're using, and you should recognize what the design of the scanner. Again, of course, this blue line is the laser, and that's the detector. That's how this scanner is designed. And there's other designs. Some of the designs called flexual design, and where there is a piezo. This is actually not piezo; it's a metal plate, and you have cuts there, and then you have piezo stacks that push the plate in moving in XY. And this mathematical formula describes the feedback. The feedback means that when the tip is experiencing a force, when the force is too high, the feedback needs to lift the piezo, and therefore to reduce the force. When force is too low, it will push down the Z height, and therefore to increase the force. And then this is PID that people always ask me, what is the P gain, I gain, and so on and so forth. And this Z arrow is the measured deflection or measured amplitude, the difference between measured against the set point. So that's why it's called error. And P is proportional. It's a number times this, and it will add a integral, which is a time-dependent integration of the error. And then diffraction is measure the acceleration. You add them together, and then it becomes this input signal of the Z piezo. And that formula describes how this input signal is generated. So again, the purpose of us is not to create a very long presentation. I'll stop right here. We'll continue next week, every Tuesday. And then thank you for your time. And this is the end. If you have any questions, please unmute and ask me right now. Okay.
How old are they now?
They are officially teenager. They're 12 and
Yeah,
12.
These are old pictures of the twins.
Yes, these are old pictures. Yes, they're Sophie is a gymnast, and she have like several pounds of medals. So Kelvin plays video game. That's all he cares.
He's still got the engineering and fixing and building gene going on.
They can naturally do that. They don't even think that's a skill at this moment. Yes.
Boy, how is Wu, by the way?
She worked for General Motors and very busy, work from home. Yeah.
Good. Glad she's doing so well. Tell her I said hello. It's been a long
Sure.
time.
Yes. Yeah. So yes, that's why we kind of like grow roots in here in Michigan, and cannot go anywhere anymore. See how to record on this computer.
And you're not traveling as much for a change. You get to stay home for a little while.
I cannot travel because in the summer I thought, oh, that's great. In the summer I'm gonna stop recording.